Hi, I'm Wada from Ritsumeikan University. I want to talk about the computational model of motion sickness considering visual and vestibular information. Okay, there is a concern that increasing opportunities to use digital devices in transportation system, including the automated vehicles, increases risk of motion sickness. So the technologies for predicting and estimating the motion sickness is required. So one of the such technologies here, a computational model for estimating the motion sickness have been developed. Fitting model of the motion sickness, including MSI and MSDV, have been developed to predict the MSI motion sickness for a simple motion stimulus, including sinusoidal motion, but that cannot be used for complex motion stimulus. And besides, there are several models that are based on the hypothesis of a mechanism of motion sickness, including sensory conflict theory or neural mismatch theory. They are promising to understand the mechanisms of with the motion sickness and to predict more from complex motion stimulus. Okay, the sensory conflict theory of the motion sickness or neural mismatch theory is known as a widely accepted hypothesis how motion sickness occurs. This postulates that the conflict among the neural signals in our central nervous system leads to the symptom of the motion sickness. The cause of the conflict should be one, a modality of sensory signals like vision versus vestibular signals, and two, sensory signals and its expected signal by internal model that is sort of built in a central nervous system. Okay, so let's think about the what kind of sensory signal should be used in as a conflict, sensory conflict. So surprisingly, no research answered that question, but the only one exception is this one, subjective vertical conflict theory, proposed by Bless and Boss, in which the direction of the gravity or verticality is used as a conflict. Yep. As a pioneer work, Boss and Bless proposed the computational model of the SVC theory that can predict the motion sickness data for 1 degree of freedom vertical motion. And this concept or this model has been expanded to more complex situations. For example, our team expand the Boston model to 6 degrees of freedom motion, including head rotation in 3 dimensions. And there is another extension to add in a visual input, but no rotation cannot be dealt with, and the model cannot be used for the measured data, meaning that it can be used for only a computer simulation, right? So therefore, in the present study, we develop a computational model that can predict the motion sickness and that can deal with visual and the vestibular input for 6 degrees of freedom motion with measured data. Okay, the purpose of the present study was to develop a computational model of the SVC theory for 6 degrees of freedom motion with vision and the vestibular input, and to develop a method for approximating the visual perception through the optical flow analysis of video images, which allows us to predict the motion sickness using camera and IMU, inertial measurement unit sensors, right? And to predict, to investigate the validity of the proposed model through a computer simulation and the experiment under different visual conditions. Okay. This is the 6 degrees of freedom model of motion sickness that was proposed by our group. And the input of the model are 6 degrees of freedom motion of the head, including head acceleration and head angular velocities. And the output of the model is MSI, that is defined as the percentage of the human who vomits with a given motion stimulus. The model includes dynamics of the otolith and the canals and their interaction to calculate the sensed vertical direction or gravity. The internal model that is thought to be built in the central nervous system calculates the expected vertical direction here, and the error or discrepancy between the sensed vertical and the expected vertical leads to the motion sickness. Okay, this is our proposed model in the present study. The red part here that represents the visual input and its interaction with the vestibular signals were added here. By interaction, the perceived motion is modified or altered by visual input. The red parts are based on the Newman thesis, right? Okay. These illustrate the simulation result for 1 degree of freedom sinusoidal motion here, for translational motion and pitching rotational motion. Due to lack of time, I'm omitting detail, but for result of the translational motion, the result is similar with the observed result in the Macaulay's experiment. I mean, both of them have the peak of the MSI around 0.2 Hertz. Okay. As a second simulation, the effect of the visual information on motion sickness was investigated. The head motion was given in pitching rotation, as shown in this equation. And we have 3 conditions as shown in this table. In A, consistent condition, the visual information was identical to the head motion. And in B, conflicting condition, no visual information was given, and which imitates the reading a book in a car by assuming, smaller gain 3 was employed by assuming that the human can decrease our weight to the visual information when we notice that the visual input does not reflect our body movement. And in C, eyes closed condition, no visual input was applied to, and also the gain k equals to 0 was used by assuming that we do not integrate our visual information to our body motion perception when eyes closed, right? And this is a result. This is the result demonstrates that the motion sickness increased when there exists conflict between visual and vestibular signals. So the similar tendency can be found in literature and our daily life. In the numerical simulation shown in the previous slide, it is assumed that the visual perception of the angular velocity here is given in advance. To calculate the predicted MSI using the experimental data, it is necessary to estimate the value here in some way. So in the present study, the mean of optical flow velocity across all pixels of the image that can exceed the threshold was used as the visual velocity. Okay. We conducted a pilot experiment to collect data by IMU and the camera to estimate the motion sickness, or MSI, using the proposed method. Okay, Arduino with camera and IMU was used to collect data. The device was vibrated for 60 seconds in pitching direction, and the maximum angle was 65 degrees, and the frequency was 0.2 hertz. And the sampling frequencies were 60 hertz and 1 kilohertz for camera and for IMU, respectively. And here, as similar with the numerical simulation mentioned above, we have two conditions for calculation. And for both conditions, the data from IMU was used for head motion input of the model. And in a consistent condition, the visual velocity measured by optic flow analysis of the video image was used as a visual input of the model. And in B, okay, in conflicting condition, no visual velocity was inputted to the model, which imitated reading a book in a car, in a moving car, right? Okay. These are the this figure shows the measured result of the angular velocity by gyro sensor and angular velocity measured by optical flow analysis of the camera image. As you can see, these have very similar shape, right? And these measured velocities were inputted to the proposed model to calculate the MSI, and this is the result. As you can see, I want to say that the motion sickness increased when there exists a conflict between vision and the vestibular signals. Same tendency as computer simulation was obtained here. Okay, conclusion. A computational model of motion sickness with visual and vestibular inputs was proposed by expanding our 6 degrees of freedom SVC model that can deal with only vestibular inputs. And the validity of the proposed model was tested by changing the visual input through the numerical simulations and experimental data to allow us to use the measured data or experimental data, a method to calculate the predicted MSI using the experimental data measured by IMU and camera image was proposed. Both of the numerical simulation and the experiments demonstrated that the proposed model can describe the result that the motion sickness increase when there exists conflict between vision and vestibular signals. This tendency of the result agrees with the knowledge found in the literature and what we observed in our daily life. Okay, future works. The predicted MSI by the proposed model should be compared to the motion sickness measured in the experiment through experiments in laboratory setting and natural environment such as riding in a car. Okay. And also in addition, the effect of the static vision such as rod and frame effect, which is important to determine the verticality of the body, should be included in our model. Okay, thank you very much for your attention.